Welcome back to these periodic seminars. Hope you had good holidays and that everything is fine by your side. We are going to start a new series of seminars today with Ricardo Severino on improving the quality of service for large-scale wireless sensor networks. He will have around 45 minutes to entertain us. He has been doing his PhD here for the past 5 years, so this will be kind of a rehearsal for his final defense at the same time. So don't hesitate to ask as many questions as you can to help him improving his presentation. Thank you very much.
Thank you. Okay, so thank you very much for coming here. Yes, the idea is to give a quick overview, or maybe not so quick overview, of what I've been doing here for the last 4 or 5 years. I've been focusing on this topic, how to improve the quality of service of large-scale sensor networks. So I'll begin this presentation by presenting the motivation for this topic, and then some of the challenges that we have to face to achieve this improvement. And then I'll tell you a very nice story about how everything was planned beforehand, and everything went according to plan, which is not exactly how it went, how it happened, as you can imagine, but that's okay. So then I'll present some of the application scenarios in which we use to validate and to demonstrate all the proposals we did, and then we'll enter into the quality of service improvement proposals here. I'll end the talk with some final remarks and by discussing a couple of future research directions that might be important. So microelectronics is probably the latest revolution in technology. This is true. Pretty much all of the devices, computing devices that we use today, rely on microelectronics. And this actually potentiated the exponential growth in computing. And so Moore's law is often referenced as a good description of this. But this paradigm has actually been happening for the past 100 years in computing. This exponential growth has been going on since the first electromechanical computing devices. Another interesting thing is the fact that if you compare today's computing devices with the mainframes of the 60s, you see an obvious reduction in size. And this is, yes, because of most of the advancements in microelectronics since the invention of the semiconductor, which led to transistor, microelectronics, and then the microcontroller, in which we try to fit everything inside a single integrated circuit, and which led eventually to embedded systems. So embedded systems are now everywhere, in everything, and you can find them in the cars, pretty much all of the home appliances, airplanes, etc. And it's now enabling what I call the smart everything. You have smartphones, smart watches, smart everything, right? So it was this pervasiveness and the ubiquity of embedded systems, together with advancements in wireless technologies, fueled by an eagerness to control and monitor everything everywhere, which actually gave birth to wireless sensor networks, from which the Internet of Things is a weird derivative. So wireless sensor networks is now enabling several applications, ranging from environmental monitoring to precision agriculture, industrial automation, etc. But there is this set of applications, which we call the cyber-physical systems, in which timeliness is of increasing importance. Communications must be not only logical or correct, but also produced on time. And this is the kind of applications we are focusing on. However, there is still a lack concerning these applications in real-world applications and fewer commercial applications, especially when quality of service needs to be addressed. There is a lack of matureness and a lack of solutions. So it is quite a bold claim to do these market forecasts. For instance, IEEE Exchange predicts a $48 billion market in the Internet of Things by 2025. That's quite amazing. So I mentioned quality of service, but what is this quality of service? Traditionally, quality of service is associated with bitrate, network throughput, etc. But this is very limited. I believe that quality of service should also encompass other things such as availability, timeliness, robustness, scalability, etc. These are all important to ensure to give the user a good quality of service. In this work, we focus mostly in these four aspects: timeliness, scalability, robustness, and energy efficiency, although energy efficiency was mostly addressed indirectly and not directly by the proposals. This is the nice story part I was telling you about. So we will try to follow this hands-on approach as much as possible and to rely on the structural health monitoring scenario and a data center monitoring scenario to validate the proposals. So we use these CPS application scenarios to identify QoS challenges and to propose new mechanisms and add-ons to address them. We implemented these mechanisms in these application scenarios once again, and we validated those in the application scenarios. So this is more or less how the work was carried out. We also relied as much as possible in the 15.4 and ZigBee technologies and in the usage of off-the-shelf technologies. Why using off-the-shelf technologies? Mostly to reduce the development time and cost, for increased interoperability, and for speeding up the deployment in real-world applications. The reasoning behind the usage of 15.4 and ZigBee is mostly related to energy efficiency, but there are other reasons, as we'll see. Although there are many other protocols that can potentially be used for this, this is the line of protocols that actually give us lower bit rate. So it's more energy efficient, and with the possibility of having adaptable duty cycles due to the beacon enabled mode of this protocol, we can have even higher efficiency. Also, its MAC protocol is quite flexible. With it, you can actually support both real-time traffic using GTS, guaranteed time slots, and also best effort traffic in its CSMACA part, so in the cap. Using ZigBee, you can also have scalability. You can support mesh and the cluster tree network, although the star that is here is not pretty much scalable, right? It is also an enabling technology for ZigBee, 6LoWPAN, wireless HAD, other protocols, and there is a big advantage in using this. That is, there are already many available tools. There are proven implementations of these protocols and tools that we can use. The cluster tree is mostly for the network player. It's quite interesting to us. First, because of its scalability, but also because all the nodes can be synchronized. Now, this is good because we can have inactive periods in all of the nodes, which means we can save energy. And the fact that it has no redundant paths is actually a good thing, because we can have predictability in the network. And although it is not commercially available, there are implementations of this. So the objectives were to devise architectural solutions for supporting real-time and reliable communications in large scale networks, relying on 15.4 ZigBee and off-the-shelf technologies, and to implement this and validate these proposals in real-world scenarios. This was actually the thesis statement. The 15.4 and ZigBee set of protocols, complemented with a set of QoS mechanisms, can effectively support the requirements future embedded computing systems may impose. So we'll now start by looking at the application scenarios that we developed, starting by the structural health monitoring scenario. So these two pictures here were taken after a bridge collapsed in Castelpaiva. Actually, a bridge that was connecting Castelpaiva to Entre, which is about a 45-minute drive from Porto. This is a passage over Doubs River. 59 people died here in this collapse. That could probably have been avoided if damage identification had been carried out. But structural health monitoring is not only important for bridges and buildings, it's also important for industrial machineries, machines, vehicles, etc. Everything in which natural phenomena, service flows can cause damage to the integrity of those structures. Of course, visual expansion is quite expensive, time costly, and installing the sensors, for instance, in a bridge and building can take over 75% of the total testing time. And this is mostly because most of the techniques we now use are wired, which make them quite cumbersome to deploy, despite the aesthetic concerns of having wires all over the place in an ancient building, for instance. This is an example of such a system that is traditionally used here, and this is something to cost, with 4 accelerometers, something to cost around 10,000 euros. It's a lot of money for this. So this limits the scale of the system. And wireless equipment is still, or at least at that time, was still in prototyping phase and not ready due to synchronization problems to do model shape analysis. You see that to carry out this, synchronization is very, very important. All the nodes must be acquiring the data in a synchronized fashion, otherwise it doesn't work. So in our proposal, we focus on having this tight synchronization and a very high sampling resolution. And you'll see why you need it. So this is an overview of the system that we designed. The first prototype has 4 sensing devices that were composed of a telescope nodes, a data acquisition board, and this is the only thing that was hardware, right? That was not off the shelf, and then an accelerometer connected to it. And there was this coordinator node, so coordinating the whole network and also serving as a sink, where all the acquisition data was being transmitted to. Data was then forwarded via USB to a PC application where the civil engineers would carry out their analysis. By the way, this project was done in collaboration with the University of Milan, with the civil engineering department, and they kindly provided us with the wired device so that we could compare our prototype to. This was also deployed in this tower in Mugadouro, and this is actually quite interesting. This is a wooden pole in a lab where you see the modes attached to it, and this is equivalent in terms of properties, vibration properties, equivalent to this tower here. I didn't know that. That's quite a cool thing. So, and we measure the acceleration. We got the acceleration readings here, and you compare them to the conventional wireless system, and it's quite close, not only for big amplitudes, but also to quite small. This is those 25 milli-Gs accelerations here. Also, for you to get a hold of how this works, there are 2 big kinds of tests. There are those where they provide some input to the system, something like this, and they measure the output. And then they have the ambient tests, in which there are no artificial inputs, and the only input to the system is the winds, service flows, etc. And so they, what they did here was to identify these resonant frequencies here, and they could be identified as well as with the wired system. So this is what they need to then use the fast Fourier transform, etc., to analyze the integrity of the structure. So there were 2 publications out of this work, and then I'll move on to the data center monitoring scenario. So the motivation is quite simple. Today's data centers are largely inefficient. If you look at how the power is spent, you'll see that almost as much power spent in powering the servers is spent in cooling down and keeping the temperature inside the room using temperature and humidity levels controls. So this is a lot of power that is being spent on this, and Portugal Telecom is building a new state-of-the-art data center, it's going to be the biggest in Europe, and this triggered a collaboration between PT and CISTER to design a wireless sensor network to provide fine-grained monitoring of power consumption, cooling, and a couple of environmental variables such as temperature, rigidity, and pressure. The applications should enable in the future to minimize local hotspots, to improve energy efficiency, and even to carry out, after using obviously some algorithms, workload management. So actually migrating workloads within the service. Okay, so this is an overview of the system. My work was mostly done within this area here. If you notice, there are several levels here. This is the sensor network layer level, and we have a gateway that is getting all of the data and then transmitting that to a database, which then is collected and visualized in a visualization Android application, I think. If you notice, there are two kinds of networks. We have a bus-based approach and a cluster-based approach. And the reason for this is that we wanted to reduce costs. Having all of the sensors wireless is still quite expensive. So we designed this approach here, in which the sensor nodes are connected to a bus. I'm not going to talk about this, because the most interesting solution for this work is this one here, in which all of the sensors are wireless. Okay. So this is a picture of the deployments of this in a data center. In effect, this is Dell USB here, connected via USB for power only. And this is actually a screen grab of the sniffer application showing the network formation. In this diagram here, you can see how the deployment was made. You have two rows of racks, and on each rack you have a cluster head, and then you have three sensing nodes in front and three on the back. Okay, so you have a cluster per rack. We also support different application modes. The normal application mode, we have a synchronous data acquisition and a report every 8 seconds. Each node reports every 8 seconds. But we can also do something like this, to zoom in one rack and actually carry out a non-synchronized data acquisition and have that rack, a higher priority rack, report every 0.8 seconds, while the others report every 2 seconds. So we can actually play with this. We can also have all of the racks synchronized and carry out the synchronized data acquisition. This is a journal publication with this work. And now I'll move on to the quality of service improvement proposals. On timeliness, there are several contributions. Two of them in the max 15.4 max sublayer and one at the ZigBee network layer. And we'll start by the top, by looking to the performance evaluation of a traffic differentiation mechanism in a real-time operating system. Why it is important to have traffic differentiation here if you have GTS? Easy. If you have GTS mechanism, you cannot give a granted slot to every node, right? So there is a limitation there. Even if you could, there could always be a coexistence problem, interference. So we cannot control that. In particular, in the data center monitoring scenario, like I already mentioned, we wanted to have possibility to zoom in some nodes or to some racks, but that is only possible if we can actually have higher priority nodes, which traffic can be differentiated from the rest. And to do that, we need to have this traffic differentiation support in the CAP, so in the computation access period. So we didn't propose traffic, that was already a proposal, we just carried out a performance evaluation, and this mechanism relies on these three MAC parameters by tuning them, then it can achieve this traffic differentiation. We carried out this performance evaluation in an ARP operating system, not TimeOS, because TimeOS is not real time, and we needed to carry out an accurate performance evaluation. We needed this real time approach. It So this mechanism also supports the FIFO queuing and priority queuing, and they were actually both implemented. So these are the results. What you see here is a picture of the performance evaluation. Yeah, this is disconnected, but don't mind that. Here you can see 4 of the scenarios that we put together, and we saw many interesting things. I'm just going to tell you about this because it will be important later on. We found out that changing the contention window of the low priority traffic up is actually what is going to improve the probability of successful transmissions for high priority traffic. So the best scenarios are those in which this contention window was changed. Yes, this is a publication out of this, the conference. And then I'll move on to the GTS implementation. There was no GTS implementation in the 15.4 timeliness distribution, and that was important for us. But implementing this has several challenges. In timeliness, we must ensure that that all the message transactions are collected scheduled, and that these transactions happen always inside the boundaries of the GTS. In terms of complexity, because this actually generates a lot of information, the GTS management table is quite big, and we do not have any memory to spare in these devices. And also in terms of responsiveness and reliability, this is a mechanism that should not fail. So I'm not going to the details of the implementation. I'm just going to tell you that we use 2 components, one for the device, end devices, and another one for the coordinator devices, just to separate things. The coordinator, the implementation is much more complex. We also were concerned by having an efficient GTS database management implementation and the capability to handle multiple requests, allocation and deallocation requests. In this picture, this thing is here just for you to get an understanding of how this component fits into the rest of the implementation. So we have a token that gives us access to the radio. So at the beginning, this component that is the beacon synchronized, in charge of synchronizing to the beacon frames, has this token. It will then pass it to the component that handles the best effort. So the CAP, the best effort traffic. And then it passes it to the CFP, so to that component that we designed. And then we have full access to the radio, both to transmit and receive messages. For validation, we use several things. We also designed a small application that is available together with the code. And this is this is just a screen capture of the sniffer application showing a GTS allocation request. Okay, this is the GTS request. This is the GTS data in the beacon payload, and you see transmissions here inside this GTS. Okay, this is we published a poster in WSM about this, and we also submitted the code to the 15.4 working group, and it's now part of the timeliness official release, and it's available in through their Git repository. So concerning the ZigBee network layer, what we observed is that there is a lack of flexibility in adapting to changes in bandwidth and delay requirements at runtime. And this is for the following reason. Usually, to schedule the clusters, we rely on what we call the time division cluster scheduling. And this is a kind of schedule that is going to remain static throughout the entire network lifetime. So if we need to change to adapt on the fly to bandwidth and end-to-end delay with different latency requirements, we cannot do that. At least without requiring long inaccessibility times and the reassociation of all the nodes. So we wanted to give a better solution, and we developed what we call DCS, which stands for Dynamic Cluster Scheduling. This is not an optimum method. That would be too complex to run in the nodes, but this is a low complexity approach that can always give a better solution to this scheduling. And in this proposal, we actually have two techniques. Dynamic cluster reordering, which enables us to reorder the position of the different clusters at clusters' active periods, and dynamic bandwidth redistribution, in which you can change the bandwidth that each cluster has. So by changing its superframe order. Starting with the dynamic cluster reordering. This is a problem that we currently face that we're currently facing at the structural health monitoring scenario. Usually you have to choose either to minimize downstream latency or to minimize upstream latency. You cannot have both. In the structural health monitoring scenario, we were trying to minimize the downstream latency to make sure that we could set up all the hosts with low latency, etc. But this schedule here is ready for that. If you have to transmit something from the sync, from coordinator to C21 here, you can do it in one run of this schedule, C1, C11, C21, low latency, right? But now imagine that you have to transmit something from here to there, and this is data acquisition, the data that you acquired. And now you have a problem because you're going to receive everything in this active period here, and then you have to wait until you get here to C11, and then you have to wait here until you get to C1 to transmit things, all the data back to here. That's enormous latency. So it would be much better to have something like this, in which you have C21 at the end, C11 at the end, and then on the next run of the schedule, C1. Right? That would be better. So this is exactly what we do in this approach. And without needing to reassociate any nodes, just resynchronization of the network. To redistribute the bandwidth here, we actually have this is more complex than obviously what I'm telling you, but I do not have the time to go into all the details. But what we do here, we start by looking for free space here. And if we don't have any, if we have free space, great, we can distribute that amongst the nodes that are involved in this stream here, for instance, from C41 to C1. If we do not have that, we need to pick up this bandwidth from the other clusters and put it in the ones that are involved in this cluster, in this stream, sorry. This is what we do here. And this is done by changing the superframe order of these clusters. And we can do that at runtime easily. It's not a problem. So this was validated in the structural health monitoring scenario. We set up 4 different scenarios. One with the original schedule, another one considering a stream from C41 to the sync here with DCR technique, another one with DVR, and another one with DCR plus DVR. And here you see the results for the end-to-end delay. So you can notice that we managed to reduce the latency from 14 seconds, almost 15 seconds, not 14 seconds, to close to 1 second. Okay, that's a 93% reduction with this technique. Obviously, as the beacon order of the clusters goes up, the difference will be even larger. Okay. Changing bandwidth, adding bandwidth to these clusters actually doesn't help much, because it doesn't matter how much bandwidth they have. The problem is latency, right? And they have to hold all the messages inside the queue and wait for service. So this is a big problem here. This is a comparison between the experimental results and simulation results, and the results are more or less the same. We have to account for the differences in the granularity of the timers of the nodes, which is intelligent nodes, which is different. Concerning how much time it takes to transmit the structural health monitoring data to the sync, if you look at a data acquisition of 5 minutes producing 270 kilobytes of data, from one cluster this would take, with a normal schedule, 45 minutes to transmit everything. When we use this DVR technique, we can actually reduce that to half. And we just increase by half the available bandwidth. But we can triple that or use multiples of that. So we can actually increase, you have better, higher reductions of this. So this is a screen capture of the sniffer application showing DCR technique, so cluster reordering technique. You see that it begins by a beacon transmitted by the PAN coordinator, and then its child's routers transmit next, these two beacons here. Then on the next period, another from the coordinator here, and then you see more devices, more cluster heads transmitted in their beacons. This is not reassociation, this is just a resynchronization. And then it continues downstream until all the network is resynchronized, and then we begin with transmitting data from the cluster in C4, that C41 cluster to the sink. It's passing, transmitting in each, so on all the cluster heads up to the sink. So we published this journal paper, conference paper, and we have also a technical report with more information on this. So we're now going to move into scalability. So how can we scale these networks? Okay, the cluster tree topology of ZigBee is scalable, yes, but some applications require more than that. Because we are actually using a time division method here to schedule the different clusters, these cluster heads do not have the same notion of time. So if you want them to start carrying out the data acquisition in the structural health monitoring scenario, for instance, at the same moment, they cannot do that. They do not know, they have no knowledge of that time, of what that moment is. So we developed this mechanism that we call scalable synchronization to do this, and it works in the following way. So in here, what we have to compute the offset in symbols from the beacon of the coordinator up to this moment, which we call T-sync, in which we want all the nodes to start their data acquisition. After we have this, we put that in the beacon payload. Okay, so it is transmitted in this beacon here. When this beacon is transmitted, the shells of the coordinator, so these nodes, these cluster heads here, will hear that, and they will compute their own offset. How? They know the offset to the coordinator, right, to their parent, so they just have to subtract from this length here their own offset. After they do this, they know the offset to T-sync, and they immediately start the timer. And this process, and they then pick up that information, they put it in their own beacon, and it's transmitted downstream to the network. And this is how this is achieved. After all of them have this information, when T-sync begins, their timer will be triggered, and they will start the acquisition. So this is more or less how this works. Obviously, we have a problem that has to do with clock drift here. The clock of each node is different, temperature is going to change this drift, and we have to account for that. So theoretically, in the worst case, for 15 clusters, which we use in the structural health monitoring scenario, we can have a maximum drift of 152 microseconds, and this is enough for our application. We did this an experimental evaluation of this using tablespoon modes here, and we measure an average of drift of 39 microseconds and a maximum drift of 100 microseconds. So even less than the theoretical drift, which is actually quite positive. So we have a book chapter about this in this lecture notes in computer engineering from Springer. And now we move on to robustness. So by robustness, I mean how the network is going to cope with the change in the traffic rate, for instance. Is it going to be able to provide the same quality of service or not? And usually it does not, so we have to support this. So we actually developed this cross-layer quality of service management framework for ZigBee cluster trees, which carries out an online control of several MAC parameters and network layer parameters to improve on the probability of successful transmissions, and this is by triggering the TRAD-if mechanisms that I've mentioned previously. and also to minimize queuing delays and memory requirements by carrying out an efficient bandwidth reallocation by using DVR. So what this mechanism is going to do is to online check the performance of the network and trigger the mechanisms to improve the performance if necessary. So this is done by the following way. You have a service access point that we developed for each of the layers of the protocol stack, and through it we're going to pull a set of counters, packet counters, so successful transmitted messages, failed transmissions, amount of messages to be transmitted at the network layer, etc. And we're going to grab that, and we're going to compute two performance indicators. TI is going to look into the bandwidth requirements of a node, and TI concerns the behavior of the successful transmissions. And these two performance indicators are going to be the inputs of an algorithm that is running here that has two parts. In the first part, we're going to analyze these bandwidth requirements and check if we need to increase or decrease the available bandwidth by triggering the DVR service. On the second part, we're going to check if we have high priority nodes. If we have them, we're going to check by looking at this TI indicator if we need to increase or decrease the traffic differentiation service, so if we need to provide a better probability of success to these nodes. And we will trigger this service accordingly. TCM is comprised of two nodes, fixed rates, in which the user inputs the traffic rate to guarantee, whatever, every 2 seconds send a message, right, something like that, and then the algorithm is going to carry out the changes in the network to accommodate that. And we have what we call the auto rate mode, in which the user doesn't care about the rate, but he just wants to maximize these rates of delivery, and just has to give a minimum performance that the network must guarantee. We also developed what we call the beacon payload management. If we notice, we have many applications that need access to the beacon payload, and we have to manage that. So we designed this is the frame format of the beacon payload, in which an ID is given to each of the modules that need access to that payload. So we can manage concurrency. And when receiving a beacon, this payload management module is going to get that payload and deliver that to the module that data belongs to. So we did the validation of this through simulation in the data center scenario. And we use here two of the modes, Raxu mean and normal mode that I mentioned previously. And yeah. So the results. Don't be scared, because this is going to be confused. It's actually quite simple. What you see here in the top is describing DI, which is the indicator that translates the amount of messages that are being sent by the network to the MAC layer, and so this gives us a relationship of the available bandwidth that we have, if all the messages that are being produced are being sent or not. So when we start with AM5 here, we are zooming in on this rack R2, what happens is that we don't have enough payload, this indicator starts decreasing. And this is going to trigger this DVR proposal that I mentioned before. And it's going to increase the superframe model to increase that bandwidth of this cluster head. So when it does that, the bandwidth starts, the indicator starts increasing again, and it remains more or less above 95% all of the time. This is what happens to TI, that indicator that concerns probability of success. So we have high priority nodes here. I've said that I'm zooming into this rack. This is what we are interested in. So this is high priority traffic. And if you notice, more or less around here, it drops. So the probability of success drops beyond 90%. And this triggers TRADIF. We're going to increase the service for this cluster head by increasing the contention window of the low priority traffic. If you remember this graph I showed you previously, what is going to happen now is this is the probability of successful transmissions of the cluster head 2, so it has these big raised here, and the other dropped, which is fine, because we are interested in this. Right? And then later what happens is that we change back to normal mode. There is no need for bandwidth. The bandwidth gets decreased. You cannot see that happening here because this indicator does not show that. But you can see that when we change tradif back to normal, when we disable it, the probability of successful transmissions of the other clusters rises a bit, and also the probability of successful transmissions for cluster R2 decreases a bit and is around the same as the others. So this is the understood vision. And you're probably wondering now, where is energy efficiency? Well, like I said, this is addressed indirectly. How? Well, TCM with tradif leads to less collisions. This means higher energy efficiency. By DCS and DDR, lower stream transmit time leads to higher energy efficiency. And obviously the choice of the 50 code for beacon enabled mode also is the choice that is going to lead to higher energy efficiency. Now, a couple of final remarks. We provide contributions to these 4 quality of service aspects: tradif, DCS, and GTS on timeliness, the scalable synchronization on scalability, on robustness, the development of TCM and PPM, and also on energy efficiency. Well, this was indirectly approached. We relied on these real-world application scenarios as much as possible for validation and demonstration, and we confirmed that the initial hypothesis of the thesis, the use of 15.4 ZigBee set of standard protocols as a baseline, combined with a set of quality of service mechanisms, can effectively support the requirements that future embedded computing systems may impose. So, what's next? I would like to rest. I would like that. But seriously now, this is also serious, but Eduardo is not here, so it doesn't matter much. The quality of service balancing framework. This is something that TCM actually brought it a little closer to us. That is to have a kind of a layer in which you can define or tune the different performance levels that you wish to get from the network, and then have the network to actually accommodate those requirements without us even knowing what is happening. So this is what I would really like to do. I think it's quite interesting. Also, we can improve a lot of the engineered application scenarios, perhaps go even further and look for a nice product design, improve on the structural health monitoring modules, and also to deploy the TCM in the data center, actually get nice results for this being deployed. So that's it. Thank you for your time.
Now we have time for a couple of questions.
Basic one. So in this data center scenario, you said that the sensors are put in the front and in the back. If you would put on the opposite sides, like if it would be on that side where the two adjustment reds are like knitting together, won't it provide more meaningful data in a sense that they affect each other in some way?
Yes, I understand your question. Well, the easiest answer is to say it's not possible, because what happens is the racks are usually in a row, so they are stick to each other, right? So you do not have room to put sensors in that space. And even if you have, that is a closed enclosure, usually on the side, so air will not drift very much into that space, and actually you will find those spaces hotter than the rest. Okay? So we found that it would be better to measure in the front where there is some air intake, okay, and at the back where you can see where you have all the fans of the the servers and all the air is coming out, probably hotter. Okay? And then you can check for a balance between these. Yes.
I have two questions. So, you told that a beacon-enabled system has more efficiency. So, what are the efficiency you speak about there? Basically, only in terms of energy, or it provides more like in less latency or something like that?
Well, the case for the beacon-enabled mode is, on one hand, is obviously has to do with energy efficiency, because you can, the fact that you can actually have this duty cycle with the beacons, it means that you can actually reduce the super frame order, right, to a minimum while keeping the beacon period very high. So you have only a very short active period. That's energy efficiency, of course. But you have many other things that are important. For instance, not really related. It's not only a problem of efficiency. It's a problem that is related to quality of service. For instance, in timeliness, because you have these beacons, you have synchronization, which means that you can have guaranteed time slots. And this is important for us because this is the only way we can actually have real-time traffic. And you have the only way to have predictability inside the network. Because you have these guaranteed time slots, you know that in that period, only that node is going to be transmitting or receiving, and you know how much time is going to, what is the latency, how much time you're going to wait for that moment. Okay? So that is another advantage of the beacon enablement. That's pretty much it. Those are the main advantages of it. If you ask for why there are not many or any commercial available implementation of it, or any real-world applications that use it, because most of them actually, the ones that use ZigBee, they rely on non-beacon enable, I mean mesh networking. Well, it's mostly because they do not address this. They do not address this timeliness problem and this energy efficiency problem in the way that we do. Okay? They are perhaps not so much concerned with it. For instance, if you have an environmental monitoring application where you just have to measure temperature every half an hour, that's fine. You don't need to worry about that, right? Because you're just going to turn your radio on for this short amount of time. You're just going to get your temperature reading in that moment. So it's not a big concern, and it doesn't matter if you receive the data with low latency or high latency, as long as you receive it. Okay?
And another question, you talked about bandwidth sharing, right?
Bandwidth sharing, yes.
Yeah. So is it an unused bandwidth which is shared or something like that? Like a white space, basically.
So what happens is that you have, so every cluster head has a portion of bandwidth allocated to it, which translates in the length of the active period, right? That we call, that is given by SO, the super frame order, right? It doesn't really matter if it is being used or not, that bandwidth, because when we're going to do this sharing, what we want is to give priority to those streams that are important to us, and they are higher priority streams. Okay. Right? Because of this, it's not very important. But what we do is we get these portions. Yeah. So what we do is that we are going to get these portions out of the others. They might be using it, but they're not transmitting these streams that we are interested in. And we know that there are a lot of data that needs to be transmitted here, and it's there, right? It's saved there in those cluster heads, and it needs to be transmitted. It needs to get out of there. So we don't mind getting this method here and increase the super frame orders of these clusters and reduce the super frame order of these ones. It's fine. Okay. Thank you.
One last question.
Mine is a bit more philosophical. What do you exactly mean by large scale? Do you have like a definition? Say like after 100 nodes, I call it large scale, or its density, or traffic, or no?
Well, by large scale, the first geographical area, so the coverage that you have.
Okay.
Okay. But obviously, if you have a large area that needs coverage, you need to increase the number of nodes.
Yes.
Right? So that brings you to another problem, to another issue, that is the density of the network. So that's another thing that is meant by scalability.
Yes.
And if you have a larger density, that means that you have more traffic.
Yes.
And that's another result of scalability. So all of it must be addressed. Right? It's not only a matter of coverage, it has to do with also with timeliness, it also has to do with energy efficiency, it has also to do with the density of nodes and how the network copes with that. Everything is interconnected. So that's why when I mentioned quality of service, I said that we have to look at it from a broader perspective, right? And not just bit rate and latency. It's much more complex than that.
Because actually, I think some of your solutions could apply to a broader type of network, not only large scale.
Yes.
Because even small scale networks could suffer some propagation issues or traffic that affect the quality of service, and then you can apply one of these solutions to address a different type of network, not only large scale. But that was the reason of my question, because what is the real meaning of large scale? Yeah.
Yes, you are right. We could apply that to other, networks with a shorter coverage. And yes, of course. Yeah, that's true.
Just one more. Because the standard 15.4 has different flavors and different grades. Have you considered the latest upgrade?
Unfortunately, yes. Well, the fact is that if you look at the latest reviews of the ZigBee standard, not exactly the 50.4, the biggest change that can impact this work in the 50.4 is perhaps a change in the length of the quotation window. Not really much, but in the ZigBee standard, they are actually dropping, without anyone noticing, they are kind of dropping the cluster tree topology in favor of mesh, and they're going to get some kind of synchronized mesh, I don't know, or they're just going to leave it open for another standard, one of those new standards that is popping up now to take that. I don't know. I believe, from my perspective, that the cluster tree topology is quite interesting, because its complexity is quite reduced. You can carry out the routing is quite easy. It relies on 43 routing. It's not very complex, and it was a very nice solution for synchronization and to have predictability. Right? I'm not sure if you can do that with the other protocols. With the other protocols that are now popping up, we cannot control that. Right? We don't know what's going to happen next. We do not know which is going to win at the end. If it's going to be one winner or several winners. That is usually a matter of profit. Right? It's not always the best technical solution which wins at the end. It's what is the most profitable. And if they could do everything they want with the 802.11